So protons on the carbon double bond carbon, normally they give characteristic splitting pattern because they belong to different environments, assuming that they are cis or trans to different groups. So here in this case, proton A will be different than proton B. So proton A will split proton B and proton B will split proton A. Again, those two, they split each other because see how many sigma bonds they are far away from each other. To split each other, they should be no more than 3 sigma bonds far away from each other. And here in this case, proton A and proton B, they do split each other. See, proton A and proton B, they can split each other easily because they are far away from each other by 3 sigma bonds. And here in this particular example, proton A is different than proton B because they are cis and trans to do different groups. We're going to arrange these protons by different names. When they are connected to the same carbon, we call them gymnals. These two hydrogens here now, they are cis hydrogens, and these, they are trans hydrogens. The coupling constant between the two trans hydrogens is the largest compared to the coupling constant of the cis and the coupling constant of the gymnal though. So let's have an example. If you have this compound over here, by the way, E means E means trans and Z means cis. So here I do have a trans molecule where hydrogen A and hydrogen B are on opposite sides. Here I do have cis, which is a Z. Z means cis. We will explain further these stereoisomers whenever we explain the alkene chapter. So in these two molecules in there, this is how their proton NMR is going to look like. So you're going to see two signals for these protons. Now definitely I'm going to see a signal for the acid and the signal for the acid, but I'm not showing it in here. I'm only showing the signal for proton A and the proton B. So proton A, since it is in this case close to proton B, and see they are different because proton B is cis to chlorine, proton A is cis to the acid. So these belong to different environments, so they are going to split each other. Proton A will split proton B into a doublet. This is N plus 1. N is the number of neighboring hydrogens. So proton A has one neighboring hydrogen plus 1, so it's two peaks. And the same thing for proton B. So you're going to see a doublet of doublets in this case. The coupling constant for the trans, and the coupling constant is the distance between the two peaks. The coupling constant for the trans is the largest. It's 14 hertz. Compared to the cis, the coupling constant for the cis is narrower. It is smaller. It is around 8 hertz in that case. So proton A will split proton B into a doublet, and proton B will split proton A into another doublet. Now take a look which one appears further downfield. Proton A appears downfield because it's connected to a chlorine, which is an electronegative element. Proton B, it's a little bit upfield because it is connected to a carbon. So chlorine, carbon. Chlorine is more electronegative. See, I moved, or I went by every atom in there. I didn't go by the whole group and say this is an acid to oxygens, then proton B will be further downfield. You cannot do this. Proton B is connected to a carbon versus proton A connected to a chlorine. So let's have an example in here, splitting diagram of the vinyl acetate. With vinyl acetate, you have 4 different types of hydrogens. You have the CH3 in here, which is going to appear as a singlet. It's going to appear at one peak as one peak because it has no hydrogens around it. So it's going to appear as a singlet, but I didn't show it in here in the splitting diagram. In this splitting diagram, I cared about the hydrogens that belong to the alkene, and I have 3 of them. I have 1, 2, and the 3 of them. Each one is going to split the other into a doublet. But when you consider the splitting diagram, you have to start with the highest coupling constant first, and then go work your way to the lowest coupling constant. Just remember that if the hydrogens are trans to each other, they're going to have the highest coupling constant. And then if they are cis to each other, it's going to have the second highest. And then if they are geminal to each other, their coupling constant is going to be the smallest. So for proton D, if I want to consider the splitting diagram of proton D can be split by proton C and the proton B. Now, proton B is a trans to it, so I'm going to start with proton B, splitting proton D, because proton B is going to have the highest coupling constant in there. So this is proton D. Proton D will be split by proton B into n plus 1, so 2 peaks. And that will be the coupling constant BD. Now each of these peaks will be split into 2 other peaks, because proton D will also be split. The peaks for proton B will be split further by proton C. And the proton C will split each of these 2 peaks into another doublet. So you're going to have, this is the coupling constant of CD. The coupling constant of CD cis is going to be less than that of the trans. See the distance in there? So you're going to see a doublet of doublets in this case for the coupling constant to JCD and the JBD. Do the same thing for proton B. Proton B will be split by the D first, and then the spins will split further by proton C. So you're going to see JBC in this case. And for proton C will be split by D first, because the cis has a higher coupling constant than the geminal. And then the resulting spins will be split by proton B, which is the geminal in this case. Then you're going to have the JBC. And this is going to be the splitting diagram for vinyl acetate. Vinyl acetate has, this is the proton NMR with the chemical shift. You're going to see the first signal normally in the proton NMR is a CH3. This is a normal signal. Now, since the CH3 is connected to a carbonyl, remember, carbonyl causes deshielding. So carbonyl is an electronegative element because it is an sp2 hybridization. So, so the carbonyl is going to take electrons away from the proton, and it's going to leave it with less electronic cloud around it. So it's going to feel the magnetic field more. Its signal is going to be shifted downfield. So, so this is why the CH3, instead of being between 1 and 1.8 parts per million, it's now at 2.1 parts per million. It's further deshielded. So that tells me that the CH3 is connected to the carbonyl in this case. It is one signal. It is a singlet, one peak, and it is one peak because it's connected to a carbon with no hydrogen. So if you apply the n plus 1 rule, that's going to be 0 plus 1, then it's going to be a single peak. Now you have your C, B, and D. When you have your alkene, when you have hydrogens that split each other in the alkene, you're going to see signals between 4 and 5 parts per million. So 4 and 5 parts per million, those signals tell me that I have an alkene in that case. And by the way, if you do the DBE for this guy over here, let's do the DBE. 1, 2, 3, 4. So this is C4. You need the molecular formula. This is 3, 4, 5, and 6 hydrogens, H6. And how many oxygens in this case? I have an O2. The DBE is number of carbons times 2 plus 2 minus the number of hydrogens, which is 6, and that is divided by 2. This is 8, 9, 10. 10 minus 6, it's 4 divided by 2, and that is equal to 2. So my DBE in this case is equal to 2. Normally, when the DBE is different than 0 and you have an oxygen in there, you immediately have a carbonyl. Okay? You immediately have a carbonyl. So I know that one of the degrees of unsaturation is a carbon double bond O. I should have another one, and this is why the other one is a carbon double bond carbon. How did I know it's a carbon double bond carbon? You look at the region between 4 and 5, and if you see a lot of peaks in there, then you would know that it's an alkene. And I know over here that I have a carbonyl and I have an alkene in that case. Okay. Now for one more thing that I want to say, the region between 4 and 5, and here it's kind of like extended a little bit. See proton D. Proton D is connected to the oxygen, so this is why it's further shifted downfield. See the region over here between 4, from 4 to probably 7.1, 7.2, 7.3. Okay, so 7.2, 7.3, all of those, they're belonging to the carbon double bond carbon, because that hydrogen D is connected to the oxygen, and that causes everything to shift downfield. So HD over in this case is shifting downfield. You will see a doublet of doublet for each one of them. So this one is a doublet of doublet, this is a doublet of doublet, and this is a doublet of doublet. So basically this graph over here is seen in there. With respect to the OH, if you have an OH, then you would see a single peak, a one peak between 2 and 3 parts per million. And that corresponds to the OH, to the alcohol. This is proton C in this case. Now, proton B will be more de-shielded than proton C. And the reason why proton B is more de-shielded than proton C, because proton B is closer to the oxygen than proton C. It is separated by one carbon, and that causes the basically the difference in the electronegativity. And this is why proton B is further shifted downfield compared to proton C. If I consider the splitting pattern, for simplicity, the proton for the alcohol is always going to appear a singlet. So it won't be affected by the hydrogens that are in the neighboring on the neighboring carbon. So the proton of the OH is always going to be a singlet. Proton B, don't consider the OH. Don't consider the OH. So proton B is connected to a CH3 in there. So that's going to be 3 plus 1. So it's going to look like a quartet. Here you go. This is going to be a quartet for proton B. And the proton A is going to be a triplet, 2 plus 1, which is a 3, so it's going to be a triplet. Always the first signal corresponds, that CH3, the first signal corresponds to the CH3 in the spectrum. And as you go further downfield, that is closer to the electronegative element. So that CH2 is closer to the electronegative element, and then you will have your OH between 2 and 3 parts per million. Now for the benzene. For the benzene, you do have mono, di, and tri-substituted benzenes. Now remember that dBe for benzene is equal to 4. So if you do a calculation and find that dBe is equal to 4, then this corresponds to 3 double bonds and 1 cycle. And that is going to be a benzene in this case. Benzenes can be monosubstituted. If they are monosubstituted, then the integration of the proton NMR will be 5 hydrogens. So you're going to see 5 hydrogens in there when you do the integration. That corresponds to a monosubstituted benzene. And the signal for the benzene normally is between 7 and 8 parts per million. Sometimes it starts from 6.5 to 8 parts per million. It depends on what the groups are connected to the benzene. If you have a monosubstituted benzene, you're going to see a lot of peaks in there between 7 and 8 parts per million. Now, if you have two groups on the benzene, for benzene having two groups, if normally NMR is used to determine the para substituted benzenes. And para is whenever you have positions 1 and 4 on the benzene are occupied. Now, normally it's hard to determine from proton NMR the meta and the ortho substituted benzenes, meaning the 1, 2 and the 1, 3 groups on the benzene. It's hard to figure those out from the proton NMR, but it's easy. It's easy to figure out the para substituted benzene because think about it. This is like an alkene, and these two hydrogens are in different environments, so they're going to split each other. You're going to have hydrogen A, hydrogen B. Why I am saying they are a different environment? Because hydrogen A is connected to a carbon with a chlorine. Hydrogen B is connected to a carbon with an OCH3. So hydrogen A is different than hydrogen B. So this is why hydrogen A is going to split hydrogen B. But I have two hydrogen A's. So this is hydrogen A prime. This is hydrogen B prime. So hydrogen A is going to split hydrogen B into a doublet, into N plus 1, because you have a neighboring of 1 plus 1. So hydrogen A will appear as a doublet and hydrogen B will appear as a doublet. So if I am looking here at this spectrum there, you're going to see a signal between 6.8 to 8 parts per million, and you're going to see a doublet of doublets. This is so important. A doublet of doublet in this region corresponds to para substituted benzenes. Now, if I want to go ahead and see which is which proton is which proton, now I know that proton A is connected to the chlorine. This is very electronegative, so proton A will be shifted further downfield compared to proton B over there, which is connected to the oxygen that is less electronegative than the chlorine. So this is corresponding to proton B and this corresponds to proton A. And then you have the OCH3. Now normally CH3s occur in the 0.9 to 1.5 parts per million, but because it's connected to the oxygen, see how it is shifted in there, how far it is shifted downfield. So the OCH3, and it's a singlet. There's no neighboring hydrogens in here, no hydrogens there. It's just a singlet. So you're going to see that's OCH3 as a singlet at 4 point something parts per million. There is an NMR table that I would like you to use, and that NMR table is really very important. So I'd like you to check this NMR table in there, and I will upload this NMR table. Okay, let me see where this NMR table, it's here. Okay, so this NMR table is very important. And this NMR table here gives us information if I have an ether, if I have an ester, if I have a benzene that is connected to an oxygen there with different R's, if the R is a CH3, CH2, or a CH. Let me give you an example over here, okay? You would need your NMR table in order to determine the chemical shift. I'm not going to let you memorize the chemical shifts, so you would need an NMR table to determine the chemical shift. This is one of the tables that I would like you to use. So if you have a CH3 that is connected to an oxygen and a benzene, I'm looking here. The R is a CH3, so if the R is a CH3, connected to an oxygen, if CH3 connected to the oxygen, so my signal should correspond to 3.8. So I should see a signal around the 3.8. So this means that my structure here is a CH3 connected to an O. And this is how you know that this signal over here, the chemical shift, corresponds to 3.8 parts per million. You simply read it from the chemical shift graph and here from the NMR graph, but at the same time you look at the proton NMR and you know that, you know what, this corresponds to the CH3. So this is why I have it at 3.8 parts per million. This table is very important, especially if you have an ester in there and you want to know is the R connected to the carbonyl or is the R connected to the oxygen? So if you have a CH3 that is connected to the carbonyl, so if you have a CH3 that is connected to the carbon double bond O, this is the CO, then the CH3 should show a signal at 2.0 parts per million. On the other hand, if you have a CH3 that is connected to the O, like in this case over here with the carbonyl, so a CH3 connected to the O and the carbonyl, then the CH3 should show at 3.7 parts per million. And this is how you know the different esters in there. There's a big difference between a CH3 connected to a carbonyl and a CH3 connected to the oxygen. Please know that a CH3 connected to the oxygen will be further de-shielded, so its signal will be further shifted downfield. And as you can see here, the signal is further shifted downfield to 3.7 compared to 2.0. Another thing is this proton NMR table, and that proton NMR table tells me exactly if I have an alkane, I should see the first signals in the proton NMR. They correspond to CH3, CH2s, and CHs. And then if I have an allylic hydrogen, if I have a terminal alkyne, where should the signal be? If I have an amine, if I have a benzene, where should this signal be? So this is a benzene, and a benzene corresponds to a signal between 6.5 and 8.5 parts per million. Now there are two functional groups that are very important and they are unique, and we can determine them easily from the proton NMR. And one of them is the aldehyde. Aldehyde um, has a hydrogen, so it should show a signal in the proton NMR. And normally the signal of the aldehyde hydrogen, this is the sp2ch stretch, it shows between 9 and 10 parts per million. So you should see a single peak in there between 9 and 10 parts per million. Now for the carboxylic acid signal is going to show between 10 and probably you're not going to see the 13, so it's going to be between 10 and the 12 parts per million. You're going to see a signal between 10 and 12 parts per million, and this is precisely for the carboxylic acid.